In today's session, we will discuss about rotational mechanical system. In the previous session, we have discussed about translational mechanical system, where you have learnt about the basic elements like mass, damper and spring. In today's session, we will take up rotational mechanical system, wherein we are going to have three important basic elements which I will be explaining it to you in the next upcoming slides. Now coming to the basic elements of rotational mechanical system, we have three important basic elements, that is a spring, dashpot or your damper, followed by an inertia element. Here we are calling this as a rotational mechanical system because the type of the motion which we are going to experience in this particular type of system is a rotational motion. So here few pictures of rotational mechanical elements which is used practically to build a system is shown. So you can observe here we have a spring, a dashpot, followed by an inertial element wherein the type of the motion will be a rotational motion. So the first basic element which is shown here is a spring. The spring coefficient is denoted by K, and here the type of the displacement which is experienced by the elements which is connected in a rotational mechanical system is angular displacement. In translational mechanical system, the type of the displacement is linear motion, and we used to represent that using x as a variable. Here in case of rotational mechanical system, since the displacement is in an angular fashion, we are representing it with the symbol theta. And as you know, since it is a spring that we are using here as the first basic element, so the type of the displacement which we are going to have on either side will be different. So when we apply a torque over the spring, here instead of force, it is called as torque. When a torque is applied over a spring, you are going to see that here we have two types of displacement which is represented as theta 2 and theta 1, and the resultant torque because of the applied torque T is taken as equal to K into theta 1 minus theta 2 if you are referring from the torque side, right? So this you need to remember with respect to the spring element which is used in the rotational mechanical system. Coming to the next basic element which is used here in rotational mechanical system is your dashpot. So here, since dashpot also experiences a torque, so if I am applying a torque here you can see two types of displacement which can occur in a rotational mechanical system also. That is also represented as theta 1 and theta 2, and this is your dashpot coefficient C. So in few of the books it is represented as B also, and the resultant torque T is taken as here as equal to C into angular velocity. So angular velocity is nothing but a derivative of your angular displacement. Here a dot indicates that it is a derivative, first derivative with respect to displacement. So C into velocity V1 minus velocity V2, which is represented as d theta 1 by d omega, here d theta 2 by d omega. Okay, so this is with respect to rotational mechanical system. The torque is taken as equal to C into angular velocity 1 minus angular velocity 2. So this is a rotational in a rotational mechanical system, this is one type of the dashpot that is used, which is shown in the picture. Now coming to the another important basic element which is used in the rotational mechanical system, which is known as inertia element. Here due to the applied torque, there is a moment of inertia which is getting developed in this particular element, which is represented as J, and the angular displacement is represented as T. So in an inertia element, the applied torque is uniform throughout all the edges of the inertia element. So here only one displacement you can see, that is theta, and resultant torque T is taken as equal to J into d square theta by dt square. So here theta is nothing but the angular displacement. So here d square d theta by dt square is considered as the value which is getting multiplied with the inertia element to represent a angular torque which is appearing here. Now let's take an example and we will see how a rotational mechanical system could be built with these three basic elements. So here this is an example which is shown here. The two inertia elements J1 and J2 are connected to a fixed wall through a spring with the spring constant as equal to K2, and J1 inertia element is connected to another spring with the spring coefficient as K1, and the two displacements here, as you can see, I am applying a torque here in this direction. So torque is applied in this direction. So when a torque is applied over a rotational mechanical system like this, you will have an angular displacement here as theta1. Since it is a spring that I have, so you will obviously have two different angular displacements on either edges of the spring K1. So here theta1 and theta2 are the displacement that we have for the spring K1, and now this is connected to an inertia element, and since these two inertia elements which are represented as J1 and J2 are connected without a dashpot or a spring, you will have a friction here which is represented by B1. Okay, either C or B, friction coefficient could be taken as either C or B. So here it is represented as B1. So that should be represented with the dashpot. Okay, and the angular displacement that is experienced by J1 is nothing but equal to theta2, and the angular displacement experienced by J2 is nothing but equal to theta3. So here we have a displacement which is represented as theta3, and since the spring coefficient or the spring with the coefficient K2 is connected to a fixed wall, here we will not have any displacement. So totally, if you can observe here, we have three displacements, theta1, theta2 and theta3. Now let's draw the mechanical network for this particular example. Now just see to it that the number of nodes in the network is nothing but equal to the number of displacement what we have in a given system. So theta1 is the displacement we have here initially, theta2 is the second displacement, and theta3 is the third displacement. Now we need to connect the corresponding elements for these nodes which are represented as displacements theta1, theta2 and theta3. So please do observe from this end. So theta1, you can see we are applying the torque T1. So you need to connect torque T1 to theta1 only. So I am connecting the torque T to the node with the displacement theta1. Now between theta1 and theta2 we have a spring element with the spring coefficient as K1. So I am connecting this here. So K1 is connected between theta1 and theta2. Now moving to the next part, we have the inertia element J1 which is connected to theta2, and J1 is experiencing only the displacement theta2. So I am connecting J1 to theta2. Now J2 is experiencing the angular displacement theta3. So I am connecting J2 only to theta3. Now you have a friction which is represented as B1 between J1 and J2. So I am connecting the dashpot. I mean friction is represented with the dashpot, and it is connected between theta2 and theta3, and the spring K2 is connected to theta2 only because the other end is connected to the fixed wall. So I am connecting directly K2 to theta3. This is how a network should be drawn by considering the number of displacement that is experienced in the given system. I hope you have followed this. Now this is very important. So before building any system equation, you need to know the mechanical network that you can draw for a given system. Now in the next part, let's take another example. Let's take one more example here. So please to observe, here we have J1, J2, J3, and now we are applying a torque here in this direction. So J1 is connected to dashpot D1 through spring K1, and dashpot is connected to the another inertia element J2. J2 is again connected to J3 through two springs and a dashpot. Now, if we try to mark the displacement for this particular example, so here we have theta 1 as the first displacement that is experienced by J1 due to the applied torque T, and now since I have a spring here which is connected between J1 and D1, so here you will have a displacement theta 2, and after dashpot also you will have one more displacement that is represented as theta 3. Now J2 will experience the same displacement theta 3 which is experienced by dashpot. So now after this we have K2, so after spring K2 there will be a change in the displacement, so this is represented by theta 4. Now this K2 is connected to J3 through dashpot D2 and K3, so I need to take one more displacement here as theta 5. Now J3 will experience the same displacement theta 5. So it's totally in this particular example we have come across 5 different angular displacement. I hope the concept is clear. So just remember that whenever you have a spring there will be a change in the angular displacement, or whenever you have a dashpot there will be a change in the angular displacement. Please do observe here. So whenever you have an inertia element there will not be any change in the angular displacement. So theta 1 is experienced by J1 and K1, theta 2 is experienced by K1 and D1, theta 3 is experienced by D1 and J2, and similarly theta 4 is experienced by D2, K3 and K2, and theta 5 is experienced by D2, K3 and J3. And now if we try to draw the mechanical network for this, I need to consider 5 nodes. So 1, 2, 3, 4, 5. 5 nodes you need to have. Now here for theta 1 I need to connect my torque and J1, so connect your torque here. So this is my T, and inertia element J also should be connected here, so it is J1. Now between theta 1 and theta 2 you have the spring coefficient K1, so represented like this. So this is your theta 1, this is your theta 2. Now between theta 2 and theta 3 you have a dashpot. So this is my theta 3, so connect a dashpot here. Done. Now for theta 3 you need to connect your inertia element, that is J2. So connect J2 here. Now theta 4 I have here. So between theta 3 and theta 4 I need to connect my spring coefficient K2. So connect it here. Now between theta 4 and theta 5 you need to connect the corresponding elements, that is D2, K3. So D2 and K3 will come here. This is my K3, this is my D2, this is my D1, and theta 5 is connected only to J3. So connect it here and join everything. This completes your network for the given rotational mechanical system. So this is my theta 1. Yeah. So this is how you need to draw the mechanical network for the given system. Now, let's see how to model a simple translational system in the similar way. Now, consider a translational system with a spring and a mass like this. Now you have a force which is applied in this direction. So if I am applying a force here, since the motion is in the linear direction, in case of translational mechanical system, the force is taken as equal to mass into acceleration. Acceleration is nothing but second derivative of your displacement. So m into d square x by dt square is taken as equal to minus k into the displacement x. Okay. So this is an example of a translational mechanical system with a spring and a mass. So here you have your applied force over the mass m. So the force free body diagram for this translational system could be represented as, this is the force experienced by the mass, this is your applied force, and this is the force experienced by your spring element. So where here Fk and Fm are the force applied by the spring and the inertia force respectively. And this could be represented in the form of an equation as F is equal to Fk plus Fm. And the differential equation for this particular translational system F could be taken as equal to m into d square x by dt square plus k into x. So this is very simple when you have a mass and a spring element, and by taking the Laplace transform for this, we can write f of s as equal to m into s square x of s plus k into x of s. So this is the Laplace transform representation for your system. Here this one, after applying Laplace transform for the force value. And now the transfer function for this particular system is given as x of s by f of s is equal to 1 divided by m s square plus k. So this is how transfer function can be evaluated for a given translational system, or it could be a rotational system. Only thing is you need to first develop your equation or differential equation for the system, then take Laplace transform, and then take the output value by input value as your ratio to obtain the transfer function for the system. Now this is with few examples with m as equal to 1000 kg and k as equal to 2000 newtons per meter. This is the value what we have got as a transfer function for the given system. This is just to quote an example. We have taken value for m and k. So this is the pole zero map for the system. So since in the numerator I have only the numerical value, I do not have any zeros here. There are two poles which is obtained by factorizing the denominator value s square plus 2, and this is the pole zero representation of the system. So this is another example where you have a spring and a mass followed by a friction coefficient which is represented as T here, C here. So the total force is nothing but equal to force experienced by the spring coefficient, force experienced by the mass, and force experienced by the friction. So this is the differential equation what we have, m d square x by dt square plus c into d x by dt plus k into x. And after taking the Laplace transform, we are getting f of s as equal to m s square x of s plus cs into x of s plus k into x of s. By taking the ratio of your output by input force, we are getting the transfer function for the system after simplification as equal to 1 divided by ms square plus cs plus k. So this is an example with the m as equal to 1000, 2000 and c as equal to 1000, and this is the value of the transfer function what we have got, and this is the pole zero diagram. So these are other few examples wherein I have a dashpot, a spring and a mass, And this is the free body diagram, and this is the transfer function. This you can try later. Same procedure we need to follow. And now this is an example of a translational system with two displacements. So x1 k m, this here we have the displacement as x2, and this is the dashboard. So two displacements are there. So x1 and x2 are the two displacements which is considered as a node here. So x1 is directly connected to the force F, and k is coming in between the two displacement, that is x1 and x2. So I am putting my spring constant here, and mass is connected only to x2, and dashboard is also connected only to x2. So this is a mechanical network, and when we are writing the equations for this mechanical network at node 1, we need to write the equation considering the nodes. So at node 1, the force F is taken as equal to, because we have the force element, so F is taken as equal to K into x1 minus x2. And at node 2, with respect to node 2, when I am taking, and when you are considering your spring, you have to take the difference as x2 minus x1. And here, since there is no applied force which is connected, so here on the left hand side we will be considering that as equal to 0, equal to k into x2 minus x1 plus mass into acceleration, so m into d square x2 by dt square, because here the displacement is x2, plus b into dx2 by dt. So these are the two node equations what we have for this mechanical network. So here we are supposed to find the transfer function x2 of s by f of s for the translational system which we have here, and this is the mechanical network what we have for the displacements x1 and x2. So consider two nodes and start connecting the corresponding elements. So x1 is experienced by k, f and m1, so I am connecting all the three elements here, and between x1 and x2 I have b3. So b3 is coming between x1 and x2, and x2 is connected to b4 m2. So here I have b4 m2 which is coming, and b2 is experienced by m2, so I have b2 here, and b1 is experienced by x1, so this is connected here. Now this is another example wherein we have a mass which is connected to a fixed wall through a spring constant and a dashboard. So this is the free body diagram indicating all the forces experienced by the mass, and f of t is taken as equal to f of k plus f of n plus f of b, force experienced by spring, mass and dashboard. And this is the resultant transfer function what you are going to get when you solve. So these are few examples which are representing practically the translational system. Here restaurant plate dispenser can be represented with a mass and a spring and a dashboard. Here this is the piston. So this is the mechanical system representation for a restaurant plate dispenser. So this is another example wherein you have two masses m1 and m2 with a spring k1, dashboard b and spring k2. So here f of t is taken as equal to force experienced by k1, k2, m2 and fb. The free body diagram representation for one node, and for the other node it is 0 is taken as equal to force experienced by spring constant k1, mass m1 and dashboard b. So this is the free body diagram for m1 and this is the free body diagram for m2, and these two are the nodal equations what we have in terms of force. So this is another example, automobile suspension, which could be represented with the mechanical system like this, where automobile body, the spring and the dashboard is represented like this. So we have two displacements here, x0 and x1. So this is how a transfer function could be evaluated for an automobile suspension. So this is just for your information to show practically how this analogy is applicable for the system. So train suspension could be represented like this. So So the body mass could be represented as M2 and M1. So here suspension is represented using the spring K2, dashpot B, and another spring K1. So this is a transfer function what we can get for a train suspension after simplification. We can just go through it. So this has been discussed already. Rotational mechanical system examples. So thank you all. So in today's session we have discussed about basic elements of rotational systems, examples of translational mechanical system, and you have learned how to find the transfer function for a given rotational mechanical system and a translational mechanical system. With few examples, we have seen how to find out the transfer function and how to write the differential equation representation for a system, and you have learned how to draw the mechanical network for a rotational mechanical system and a translational mechanical system with examples. And we have correlated the same concept with few examples where we have considered an example of a plate dispenser, automobile car, a train suspension. So I hope you have understood the concept what has been taught in today's session. Thank you all for your precious time. Jai Shri Gurudev.